Hi, everyone. Welcome to Foresight's Molecular Machines Group. We've had so many seminars in the past few weeks. I'm really delighted that we have so many great nominations from so many people in this group. So please keep them coming. We are currently working on the program for the third quarter. And so if you want to nominate someone, this could be yourself, it could be self-nomination, to present and share your work, then please let me know. Today, I'm incredibly excited to have Stephane Redon here. I think Stephane and I met about a year ago at our Molecular Machines workshop, and you presented your really incredible Samson tool that many people can then have started using since then. I'm really just excited to hear more about it, like an actual deep dive rather than just the 7-minute presentation that you gave at the workshop. You've also since have become a Foresight Fellow, and it's been just a pure joy to have collaborated with you so far. It's been really, really wonderful. Thanks for all the work that you've been doing also for us. And I think I want to show people just one really fun fact of what this collaboration has recently entailed. So I think many people here are well aware of our Foresight Feynman prizes. They are currently open, and so please get your nominations in. The Foresight Feynman prizes are really working to kind of like award outstanding work in the field of molecular nanotechnology. We've had a few really fantastic winners in the past, including Fraser Stoddard, who then went on to receive the Nobel Prize for very similar work that we awarded in 2007. Anyway, short and sweet, Stephane has designed a really wonderful moving molecular gear, and it's moving even. So really, 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 really excited. Thanks so much for doing that. We're really, really happy. And thanks everyone for joining today's seminar. Really excited to have Stephane here. I'm going to share also more info on the Feynman Prize in the chat in case you guys want to apply or nominate yourselves or someone to actually win this prize. But this is enough for me and enough housekeeping. Today we have Stephane here, and he will be discussing recent developments in integrated molecular design. And I think this is a topic that we always come back to. It's very, very difficult to kind of like actually integrate all the work that you guys are doing. And so thank you so much for joining. The stage is yours. I'll be monitoring questions in the chat, and then we'll have thank you for joining, Stephane. It's a pure joy to have you on again.
Thank you very much for having me. So I'm actually not going to do a traditional presentation with slides. I'm just going to show the software, and it's not even going to be super long because I would like to discuss with people and ask questions myself potentially, like to see what people are focusing right now. So let's see if I can share my screen. So I want to share 2 screens. Okay. So if you don't know, we used to be a research group at INRIA, which is the French Computer Science Institute. And our goal at the time was to make software for molecular design. But we quickly realized that it was like an infinite job. And because the field is so complex, like even on the science, like not computer science, but science part, like the biology, chemistry, physics, it's so wide that it's impossible for a group to do everything. So that we decided to try to make an open platform with an open architecture and with an extensible way to add things. And so the way it works now is that and then we created a company to transfer that work. So the way it works is that you have a core that's called Samson. It's free. You can just use the starter plan, and then you add the extensions that you need to do stuff depending on your field, on your needs. And if you also code, you can develop your own extensions either in C++, and in this case, even if you're programming in C++, you can already distribute them online. So for example, you could use that to graft molecules on a surface, potentially a nanoparticle surface, do boxes, build stuff, do docking if you work on drug design, do DNA origami with this extension, do protein structure prediction with an extension that's actually included. Like the vast majority is free. And if you want to develop things, you can actually commercialize them. That might be a different way, even in academia, to fund some research. And what's coming now is that we're making Python more available to everyone using Samson by shipping it inside Samson. And so you can also develop Python extensions, and you will soon be able to share these Python extensions on Samson Connect as well. And so I'm going to show Samson, like basic functionalities and some new functionalities that we're adding right now. But again, I don't want to spend too much time on them because I prefer to make it a bit interactive. So just change the interface, the Zoom interface. Okay. So Samson, again, is a platform that you customize yourself. And so you have some of the traditional functionality for modeling. And first, I'm just going to show visualization. So for example, you could open a structure, and of course, you can use Samson to make images like sorry, I have to move the zoom interface because it's interfering with the, sorry, just moving into the bottom of the screen. I'm not sure you're seeing that. Okay. And then you can, of course, apply visual models to your structures. So for example, let's say, or even biology menu, you might want to see the secondary structure, hide this all atom representation, or you might want to visualize a Gaussian surface, color things based on hydrophobicity, based on chain IZs, colors, etc., etc. So many things for, like many traditional things for visualization, making images for your papers, or communicating with colleagues or presentations. Then what you can also do is, beyond visualization, you can do animations. So for that, I'm just going to open another example that's provided with Samson. For example, here I have a HIV protease structure, but you might see that we see something here. But inside the document, so by the way, this is the hierarchical view of the document. Here I have my protein, the two chains, the residues, backbones, etc., etc. But here I have a presentation, and let's close this for now. In the presentation, I have some tracks. So if you know Blender, you know what this is. I can play this animation, and this is like a docking animation that I want to explain that my ligands here go inside the active site of the HIV protease. And I can customize all this. For example, I could say that at the end of the presentation, I want the camera maybe to be closer to the binding site, or farther away, or just move it here. And then I can just interactively change this. Let's say I want to make it closer. Then by the end, etc., etc. I could also move the keyframes of the animations. For example, here, when I'm here, I see that this ligand is moving from one position to the other, but I can change the timing of this motion. So that's the second type of things that you can do with Samson, like doing animations. Let's close everything. Then a third type of things that you can do is construct things. And you can construct using atoms, like by building progressively. Let me remove the node information. And potentially minimize at the same time, and edit the structure, and go to other energy minima, etc., etc. Or use building blocks that you assemble. So that's yet another way to build. You can still minimize. And of course, you can make things more and more complex by just copy and pasting things, assembling, etc., etc. The system, then move them around, build more and more complex systems, etc., etc., that you're then going to simulate. Let's close this. Another way that you might want to build things is, instead of assembling fragments and potentially minimizing them, you might want to use some extensions that are more procedural. For example, YouTube. So one thing, I'm showing you a version that's still in development and that's not out yet. So I don't have all the extensions that are here. You have this nanotube creator, where you just click in the interface and you create the nanotubes, or you enter the parameters in case you want to have like precise construction, etc. And then potentially you edit their structures using other editing tools. But let's show that, for example, on a protein. If I take back the structure, I could say, let's take a more complex one. Okay, this one has several chains. So you could say that you twist structures, meaning you add some constraints on some parts of the structure. Like, for example, this I want to not move, and this I'm going to add. And you can fold this helix, make it move here. I could also decide that potentially I want to fix that part. Let's select several parts. And then I'm going to move the loop, reorganize the side chains, etc., etc. What's happening here in the background is some local minimization that tries to preserve the local structure and to make realistic deformations as much as possible. But to make it fast, of course, you have to make a trade-off between realism and speed. So that's one of the ways that you can build things. But of course, you can also use some prediction algorithms, like structural prediction algorithms, if you work in structural biology. And one of them is, we integrated actually several possibilities like AlphaFold, ESMFold, and we're currently collaborating with NVIDIA. And so we're going to integrate several of their tools in BioNemo. And one of the tools that we integrated from them is OpenFold. But I'm just going to show ESMFold because this one is super fast. So I'm just going to enter something that I hope will be an existing, something visible. And this is my predicted structure. So of course, in the middle, it was not structured. And so that's why I have this. So I could say, let's select at the residue level. I'm selecting these residues. And then I could move this part. And then let's say that part. So this is a new version of the Twister editor, which now makes it possible to rotate parts. And so we can make this work with any type of atomic structure. One of the things that we're doing, and that's new, is we recently released these extensions for like building polymers, assembling boxes, grafting, etc., etc. And we're now making it work with coarse-grained atoms. So there is a new type of atom inside Samson. So I'm not going to open a coarse-grained molecule, but I'm just going to, let's open back these predicted structures. What you could do is just select, so it's not going to be realistic at all. Just to show you inside the inspector, just to show you that it exists there. Sorry, interface, inspector. You can now have, so select the atoms level, and you can now have coarse-grained atoms. So of course, now that's making the secondary structure disappear. This again is not a realistic example. You're going to have access to tools like Martinize and stuff directly in Python inside the interface. So that's one big change in Samson, the possibility to deal with coarse-grained models that's coming with this new version. But one big change that we're very excited about is introducing AI. So of course, you know that you've heard about ChatGPT, generative AI, etc., for protein design and stuff. And so one of the first things that we do is in this interface here, we have this assistant. And it's basically an augmented version of ChatGPT. And what I mean by augmented is two things. First, it's specialized for Samson and the Samson documentation and the documentation of all the extensions of Samson and on molecular design. So that's the first difference. And the second difference is that, so in the background, it's like GPT. And second, it's not only an assistant, it's also an agent. So I'm going to show that step by step. I have two ways to enter questions or queries or commands. Sorry, moving the Zoom interface. Either I type or I speak. So I'm going to speak. I'm going to click on the mic and I'm just going to speak. And then I'll click again on the mic to send my message. Hey there. I would like to make an animation of a ligand being docked into a protein. How can I do that? So then it's building the answer based on the documentation of Samson and the commands, the actions, the menus that exist in Samson. So for example, here it's telling me that I can use the dock animation in Samson. And it's actually this command here. So let's say dock, let's open the animation and clean it. So I'm just removing this. Sorry, let's undo that. Play to the end. And now I remove it. I remove the second ligand. And now I see that here there is this dock animation. It's telling me how to use it, but I can also go on in the documentation. It's also telling me about related things. Potentially, I might be interested in docking. And so in this case, it's telling me how to dock using Vina, the Vina extension in Samson. So that's one thing. And I can continue as like that. So thank you. How can I make the labels bigger inside Samson? And I can ask like that about anything that's present in the documentation, because we've taught the documentation to Samson here. And so we're trying to integrate this type of help in different places in Samson. And one place where we're integrating that is, for example, for selection. Because normally, if I want to select things, I have to use the selection language. And traditionally, that's something that's super difficult to do in molecular design. If you want to have something that's powerful, where you can really control finely the selection despite having essentially thousands of atoms, you might need a complex language with node attributes, etc., etc. So I can show you, for example, how it works. You have to use attributes spaces, attributes, etc. Then logical operators, topological operators. So it's potentially very complex. But one way we're integrating the AI inside is just by saying, so for example, to select atoms, I would have to type, node.type atom, or a short version like n.ta. And if I want to select oxygens, I type O. If I want to type, let's say I have a selection here, I would have to type an S to say the selected nodes. And if I want to have all atoms within 5 angstroms of the selection, I would say NTA within 5 angstrom of NS. But that's potentially a struggle to find how to do that. So one way is I can just click now on this and type all atoms within 5. We don't have a mic here yet of the currently selected nodes. And normally it should translate that into this, what I was showing you earlier, like node type atom within 5 angstrom of node selection. So that's already a little thing where it's an agent instead of just an assistant, because it does things instead of, it does a translation, it does something. But I can use that also as commands here. I don't know if you saw in the beginning, there is one way to, instead of just asking questions, to make it do things, and is to enter a slash, where here I have a list of commands that I can do, that I can use. And so the one I just used basically is NSL. So NSL means node specification language. And with NSL, I can convert, I can get the NSL expression that corresponds to a natural language query. So here it would tell me that my query corresponds to the following NSL expression and node.type atom. But I can make it select what I want. So I can say select the binding site. And it's going to tell me that this query corresponds to the atoms within 5 angstrom of the ligand. So I see that some parts here is selected, and it zoomed on it. It selected the atoms in it. But now that we have that, we can also make it try to reason. Since it knows the list of commands, we can ask it to use them. So I can say, do zoom to the binding site. Sorry, I'm a bit improvising. So doing the /do and then zoom to the binding site. So normally, we'll see if it works. It should select the binding site using that, and then it zooms on the selection. And then I can do things like color everything in pink and apply a van der Waals model. Sorry, I didn't do. Sorry, I just copy paste that. I didn't say do. Or I don't know the equivalent name of the game in English. And so it's telling me how to do it, but I prefer to be lazy. So it applied actually. No, I'm not sure it colored everything in pink, actually. Maybe this part, yeah, is not selected because it applied the coloring to the selection. So you see, it's not perfect yet, and that's why it's not yet released. But it's going there. And one other type of command that we're working on right now is, of course, since we're integrating, since we're shipping Python, is helping with Python. So I can do things like script. Oops. Let's say select all atoms and move them in the Z direction by 1. And here it's using the documentation of the Samson Python API to generate a Python script that I can then execute directly or copy and put in the code editor. So here I see that it's importing Samson. It's getting the active document, doing a selection of all atoms, and then changing the position. So adding to the Z direction 1angstrom. And so I could copy that code and go to the code editor and paste it here, use it as a starting point. So this, if you're a geek like me, you might be using Visual Studio Code, and maybe you know that Visual Studio Code has an open source editor called Monaco Editor that's very powerful. And so we integrated that inside Samson. So if I save that test.py, now I have the color coding and I can use basically the functionality of the Monaco Editor directly inside Samson, execute the code, etc., from inside Samson. So that's one thing we do with the AI is using this to script. And then, of course, since it's Python, you're going to be able to combine that with other Python things. So, of course, we're super excited to add other commands. If you use Midjourney, I think it's like /imagine. So imagine if we if we begin to do commands like imagine and do protein design, molecular design in general. So that's one of the things we want to do. And actually to discuss with you about other things that you think might be useful, that you might need without me influencing you too much for the answers. So that's basically it for the recent things. So the fact that the coarse graining is arriving, shipping Python, and this combining AI, and the fact that the AI knows the documentation of Samson of all the extensions that are inside. So this means that even if you have a complex extension, potentially you're making it much easier to use thanks to that. Like, for example, I could say how do I prepare my system? Sorry, let's be lazy. How can I prepare my system for molecular dynamics simulation with GROMACS? Normally, it should point me to the GROMACS documentation, some commands that are in Samson. Like, for example, if I click on prepare here, it asks me whether I want to remove alternate locations, ligands, blah, 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 and tutorials, because we have tutorials about working with Samson, and of course, documentation like GROMACS step 1. So this means that, if you develop extensions and you give the documentation of it, then the Samson AI can learn it and then tell others how to use your extension. So that's mostly it. So yeah, I would love to have your opinion. what you think we should develop next. Let me stop the sharing.
I have a question.
Yeah.
Do you have, or can you have some ability to select, say, a ligand or a small collection of the atoms and do some DFT?
Not right now. There is no DFT extension right now. So when we were a research group, we developed DFT code, but it's actually not a public extension. So there is no DFT code. So no, that's the short answer. A slightly longer answer is that we think that probably with Python, it's going to be easy to generate an input of existing software. So that would be the first step. And we are actually discussing with potential partners to integrate their DFT code. But we would love to integrate like Psi4, Quantum Espresso, a DFTB, actually.
Thanks.
Wonderful. We already have two more people. Oh, we have two more people on the queue, Tomo and Ben. Unless, Stephane, you want to ask Pierre another question. Go for it. This is an open discussion. I'm only
sure, yeah.
Sorry. All right.
Is it my turn? Sorry. Okay, thanks. Yeah, so my question is coming more from a mix of business and academic background. So for adoption of a new tool like this, I think the AI stuff is amazing. But
Thanks.
Even then, yeah, I mean, that's really slick and smart. Like if you have somebody in a wet lab that's really doing much more kind of experimental stuff, but realistically, even at top universities, it's very hard for them to find a good collaborator or find a good student to.
Sorry, I don't have the sound anymore.
Sorry, you broke off after you said a good student too.
Oh, sorry. Yeah, it's hard to find a good student who can pick up these tools and stay in a lab. And I was wondering, as a part of a business strategy and to increase adoption, would you consider something like having some of your developers do consulting for this software and also rent out computing power? Because I feel like tool adoption that, getting the people in and, the AI would be helpful for somebody that's super tech savvy. But if I think of a grad student in a lab that's doing mostly structural experiments, I think they would need somebody that's basically a consulting scientist from your companies. Would that be something you would consider?
Thank you for the question. I think it's a smart question because I'm trying to be nuanced about the answer. It's complex. So for now, I can only try to predict what the direction is going to be. We actually hope that the AI is making Samson easier to use, because instead of trying to guess where the buttons are, it can be a bit intimidating to see a new interface and new tool. And so if you just use natural language to interact with the software, it might be easier to learn. So we're hoping that it might actually shift a bit the market to talk about business to include more experimental people, because we see that one thing people like in Samson is actually the fact that you click the visual interface instead of using command line to use the tools. About consulting, we already do that. That's one thing we do a lot. I showed the extensions on the marketplace, and we actually do custom development of extensions for both academic groups and pharma companies, and they sometimes end up not being visible because people just want to keep competitive advantage, or it's really working on proprietary extensions that are used to, let's say, interact with proprietary databases. Let's say you're going to click on something, on the target in your database, and that's going to open it, and so that you're going to do stuff with it. Some extensions end up being public on the marketplace. We actually developed a polymer builder for biotech, which works on coating, and they have to build polymers, and they asked us to develop that. So yeah, we do this type of consulting when we are competent. If we're not competent, we're just going to tell you, no, sorry, we don't know enough about that topic to be useful.
I see. Yeah, and I totally agree that AI is the future. It's just, yeah, kind of the initial hesitancy of a lot of experimentalists when
Sure.
I don't, yeah. So, thank you.
Wait a minute. Isn't it the case, the AI is very cool, but for some of these things like selecting molecules and zooming, I mean, an expert user doesn't need to use that stuff. They just click and drag and they're fast. Isn't that the case?
I would say not always. Like, for example, even if you're expert, if you're expert to the point that you know the selection language and you're able to type like not NTA within 500, sure, of course. And our goal anyway is not to remove this functionality. It's just to make it more usable, like more democratic too. Like everybody can visualize molecules, build stuff, like a bit like Midjourney. Everybody can make nice images. You don't become an artist, but maybe a bit. And just makes it more widespread, more accessible. For us, with this type of general tool, it's really more about access, democratization, ease of use. But then we want to, and that's why we're also working right now with NVIDIA about like BioNemo tools, OpenFold and stuff. We want to give the AI access to all these expert vertical tools, which gives it superpowers. Instead of, you could say, well, generate an assembly along that backbone. Personally, having the possibility to just click on the mic and speak, for example, makes me lazy. I don't even want to type anymore. So, but there will still be expert users. Let's just go faster, I think.
Okay, we'll leave it at this for now and move on to Ben, then Tad, and then Alex.
So I guess my question is, I don't, you showed off a whole bunch of features. I don't understand what is the intended workflow here, and what are people using it to do, and what would you like people to be able to use it to do?
So maybe the workflow in the demo was a bit confusing because again, it's an open platform, and so people build their workflows. So like, for example, some people either are going to fetch a structure from the PDB and then prepare it for simulation, or just fold using ESMFold or AlphaFold, or then use GROMACS, then use Python for analysis of the trajectory. But that would be somebody who does.
I'm asking about something higher level. So is it people who are trying to figure out, that's what I'm trying to like. What are they using it for in their broader workflow?
Okay. So if the question is about a higher level point of view, big picture, maybe it's possible to split people into two categories, like people who want to understand and people who want to create. And so in the understanding side, and people who do both, but understanding side, like some people want to understand biological mechanisms. So you have to get structures, analyze them, analyze interactions between structures, and this could be in bio or in materials, chemistry. And you have some people who want to create, people who do DNA or again creating new materials, doing protein design, and people who do both, because to be good at protein design, you have to understand proteins. So that's one higher level view. And if
and then what does this like? So for people that create, sorry, I just I don't have a good sense of what the limits are, right? In the sense of I don't think that you can say, like, if you wanted to say create a new enzyme, it's not it can't model things to that level of this fidelity. So I guess I'm just trying to wrap my head around what does it let people do that they couldn't do before?
If you look at the micro level, that just selecting, it depends on your own level, and it depends on when in time you look, because it's a bit as if you were saying, okay, what with the current existing tools, can I build a house? Sure, but it's going to be some levels of steps. Several steps. And so the more the tools progress, and the simpler it's going to be for people to do stuff. So right now, no, you cannot say, build me an enzyme or solve cancer. But hopefully it's making it easier for people to access existing tools, assemble them. Instead of coding, you can ask for scripts that assemble tools that do pipelines. And I think that's progressively, it will be more democratic.
Okay. So can I ask the question like one more different way? Like, who are the people who are really who like spend a lot of time in this tool?
Currently, you mean, inside
Yeah.
Samson? It's again, I am having trouble to answer because it's very varied. There are users in 120 countries. We have clients in 30 countries, and they do very different things. I mean, it's mostly structural biology and drug design and like bio. But
Okay. So
right now, but that's
okay.
because that's mostly historical because of the current list of extensions. It's
okay. All right. I'll drop it. I just
sorry.
I'm
sorry. We can chat after
Yeah.
because I don't understand the question.
I mean, the question is basically like when you have a tool that can do anything, it ends up being used for nothing. And like tools become really powerful when they can, like, yeah, like that's and so I've just tried to like really understand like where sort of like the serious context of use is.
Okay. Sorry, I don't believe at all that when your tool does everything, it can do nothing. I mean, like Word, Microsoft Word, or Google Docs, you can write any type of text, and it's used to write novels or technical articles.
Right, but like the original, but this isn't Microsoft Word right now. This is like early word processor, right? And that did have specific people who are using it, and so like professional writers were a clear example of the people who like spent a lot of time in it before it was like everybody using it for everything.
Now it's drug designers and pharma companies who want to visualize, analyze structures.
Okay, like that's more for what I'm getting at. Anyway, I'll drop it.
Okay.
You will also meet again at our workshop, and I think that's a good kind of like opportunity to really drive down on like making this really integrate. Okay, with Ted and
I think we can discuss about that for hours. It's super interesting.
4 hours, yes, I'm sure. We have Ted and Alexis next.
Yeah, thanks. So I'm Tad Hogue. I enjoyed you giving this demonstration of this audio help. I think we're going to see more and more of those kind of tools to help new users get going. So my question is, and maybe a little bit more of a specific follow-up to what Ben just said. And I was wondering if this tool is mainly limited to proteins and other biological molecules in solution, or could it also extend to, say, diamondoid molecular machines that Forsyth has been talking about for a long time? Or would that first need some significant additional development of interfaces, say, for specifying new types of structures or force fields, or what would be that kind of process for extending it to other kinds of molecules, non-biological?
Mm-hmm. I think you're talking about the field in general or Samson?
Samson, because this tool in particular seems like a really powerful, nice user interface for designing molecules. I'm just wondering to what extent it's very much focused on the biological things, which certainly makes sense because that's what most people do. I'm just curious.
No, but I mean, that's really historical. That's really historical in the sense that we cannot develop all extensions at the same time, but the community is still small and there are not that many people who develop extensions. And we believe that more people will write extensions as soon as like the extension store is also available for Python, because many more people do Python. And if we make it easy enough to share Python. So I think in the field, there might be enough tools already to do material modeling, like with TFT, quantum mechanics. Samson can already, I could share again, Samson can already be used to build, sorry, just share, maybe just the website. Like you have tools, polymers for graphene, and I showed you how to copy, paste, move, edit. You can already build diamondoid structures easily. Then for simulating them, if it's pure carbon and hydrogen, this force field is very, very realistic. Like the Brenner force field we implemented. So we developed adaptive algorithm for that to make very fast simulation of, oops, I think just that. Yeah. So, well, maybe done Brenner. So I really don't know how to type anymore. Okay, so it's not this one.
It's the Rebo potential, right? reactive.
Exactly. So that's a new version of the Ribot potential, but it's exactly that. Yeah.
Mhm.
Exactly. That's second generation Ribot potential. So this force field is very realistic for the geometry, less for the energy barriers. For the geometry, it's very realistic, and you can use it interactively. So I'm sorry, I don't have it in this demo because it's the one that's not yet out, and I don't have the module here.
Oh, but so it looks like your point is it's relatively easy for people who are knowledgeable about these tools to write plugins so that it will fit into Samsung. Is that?
Yeah, because you have tons of resource documentation. You have tons of documentation, tutorials about how to build extensions. So for now, it's in C++, but it's going to be, and you could already script, but it was only in the professional plan, so it was not free. But now it's going to ship Python, and you're going to be able to code in Python. So that's actually the old public documentation, but this one, I'm giving you the secret address, secret for now. So that's the new documentation. So it's going to be very easy to use that and use it for any type of structure. So it's really more historical. Again, the main point of Samson is to make it easy to integrate new things and combine them. So you could, if you have an appropriate force field, simulate interaction between graphene and proteins, for example. But that's going to be very
yeah.
create your system.
Thank you.
Wonderful. We have Alexis next.
All right. So thanks so much, Stephane, for the demonstration. That's really, really cool, I think. And I just wanted to comment and say that, it seems, in the field of protein design, I could totally see how that could be extremely useful for a lot of people as, it's becoming like more and more democratized, right? So it's like all these like tools that come out and people keep asking me how to use them, right? And I think it'd be super powerful if you could have maybe a demonstration of, integrating all the new machine learning tools for design, in like a simple kind of like pipeline with your software. That'd be absolutely amazing. So if you wanted, to really convince people, it's just add diffusion and PNN, hallucination, all that stuff. And that's, I'm sure you could do that in 2 days.
That's in the to-do list.
And honestly, I'm an expert and I compute and I can do all these things on the command line, but I'm sure I could I'd be happy to actually design, on a GUI like this. That'd be very useful even for experts. So I think it's very cool. I'm very excited to see.
I'm very excited to integrate like protein MPNN or like what's the name of the latest one you released and that got everyone excited?
Yeah, the diffusion models. So,
but is it called the diffusion?
No, it's called RF diffusion. That's like the model we have. It's called RF diffusion, result diffusion.
Yeah, I've seen a demo on Hugging Face or protein MPNN and that's great. But one issue of Hugging Face is it's not integrated. So once you have that, you have to export it and then use it in another tool. But having this type of things and you just create directly in the environment and then you do other things with it, simulate stuff.
I think that'd be amazing because I get people that ask me all the time how to use those tools, right? Because everyone is putting the code and they want to use it, right? Like non-experts. And so if you could have that, I'm sure you have a lot of academics and that'd be extremely interested to use it.
I know. I mean, we just have too many things on the to-do list, but I would love to draw backbone and then like maybe edit it with Twister and stuff. And then we say, okay, now that we have this backbone, design the sequence that falls into that, this sort of things. So many things to do.
Very cool. Thank you.
Could I ask a quick question? Could you drop in the chat maybe the Hugging Face bit that you mentioned? I would love to check that out.
I will try to find it.
Thank you. We have so many more questions, so I will try to run through them. And Tomo, since you already asked one, I'm going to go with Michael, and then back to you, Tomo. So Michael, you're next.
So it was by Simon Duer. I'm not sure about the pronunciation. I'll put it in the chat right now. It's this.
Thank you.
This link. And I would love to have something like that, but inside Samson, based on the tools by Alexis' team.
So should I ask?
Hi, Michael.
Oh, okay. Hi, Stephane. Really cool work as usual. And I have 2 technical questions. On one side, you said it's adoption of ChatGPT's algorithms, and they are not free. So how is that translated to the openness and basically a free model of Samson? And on the other side, so probably used GPT-3 to build this agent. And can you comment on how difficult it was to train it and possibly what you used?
Okay, so I don't want to give all the secrets.
Sure.
But I will have most answers on that. So it's actually cheap. GPT 3.5 is 0.2 cents per 1,000 tokens.
Mm-hmm.
And so we have not decided what the pricing model will be, but probably, what's sure is that the documentation part will be free. And you can ask as many questions as you want. And maybe the agent, like the commands, like the / something, will not. And also what might vary will be the underlying background model, like a GPT 3.5 or GPT-4. Because the thing is that GPT-4 is much more expensive. The price is different based on the tokens in the prompt and the tokens in the in the output. And it's between 20 and 30 times more expensive. So it's not feasible to make it free. And it might not be necessary. Like we try to put prompts that are clear enough that GPT 3.5 can answer. But we think that maybe in the pro plan, people will have the option to switch to GPT-4 to have, let's say, maybe better scripts, for example, when they want to do more complex things.
And
have you... No,
sorry, Alison. Have you possibly tried out the free models like Llama and the other stuff around?
Yes.
Not there yet?
No.
Okay.
No,
Thanks.
we are. Not on this.
Mm-hmm.
I also do want to say that, probably if you contact OpenAI for free access to the underlying GPT-4, they maybe are, inspired by the project and maybe able to give access to that. There's plenty of people around right now who are playing with it.
Mm-hmm. We have access to GPT-4. We see a clear difference.
Yeah, but it's not free right now.
No, it's not free. No, but even GPT 3.5 inside Samson is not free because we don't use the website ChatGPT. We use their API. And so we have to pay for that. But since it's so cheap, we want to make it free for everybody.
Okay, I also just dropped a listed here in the chat, which I usually find useful for like context on papers and so forth. So maybe there's a further extension that you linked out to listed. And I know the people there, so if it's useful, I can maybe make an introduction and see if it's useful. Okay, we have Micah up next, who I haven't asked a question yet. Micah, we can't hear you.
Yeah, I don't hear anything.
Alternatives, you can make up your question in the chat and I'll read it out in case we have time. Tomo, it's your turn again.
Hi, thanks. So how much of this software is basically you have a scientist who knows what they're doing, design a molecule and see how they bind? And can you do kind of AI-based optimization? Let's just say there are certain constraints and there's a target molecule and you want to design a molecule that binds. It has to be certain constraints, like it has to be synthesizable or it's amino acid based and so on. Could you add a feature like that uses AI to kind of replace the scientist almost?
Yeah. So for now, it's not possible. For now, the AI would just tell you to use Autodoc Vina on a selection on your own. So you could let's say fold a peptide, maybe using AlphaFold, and then try to dock it using Autodoc Vina, and then maybe simulate that, let's say with Chromax, to see how stable the binding is, these type of things. But that might be version 2 or 3 or 4 of the Samson AI. What we want to do next is something related to, maybe you've seen AutoGPT or like Baby GPT or Baby AGI, these type of things. So it's very interesting how it works. Basically, you ask it to make a plan. And you've seen a baby version of that with the do command. So in the case of the do command, I ask it to think step by step and generate a list of things to do. And there was so first I should select because everything is applied to a selection, and then I color and etc. And we could add the possibility to have a loop. Conceptually, it's not that much more difficult to have a loop and think about what to do next, etc., and continue until the objective is achieved. And potentially this could be combined. So what's nice in this architecture is that, I mean, you can ask it to use extensions. So the glue is going to be done by the AI, but the real smart things is going to be done by the diffusion models, the design model, the folding models, the DFT calculations, and then it's just our goal is just to make it easy to use. But you still need the smart people who do the algorithms and who integrate them.
Right. Okay. Yeah. So it sounds like if we wanted to design a molecule that would do a certain thing, it would almost be like the extension would have AI as a replacement for the user to run the scripts and do that. Is that what I'm hearing?
I mean,
like in the future, maybe.
Yeah, I mean, I think in the future, tools are going to be more and more powerful. And with just a few user actions, you're going to have the possibility to do more complex things. Like now we press a button or two and it cooks a chicken. And yes, I mean, that's the general trend of technology. So.
Okay, thank you.
I can stay maybe 2 more minutes longer. So Micah can ask the question, and then I have the obligatory question of how the people in this group can help you. So already get ready for that.
Or maybe just typing the question.
Yeah, Micah, we still can't hear you. So maybe I'll ask my question now, and you can put yours in the chat, Micah. If people in this group are excited about your work, then what can they possibly do to support your specific efforts? If you're looking for collaboration, funding, if you're hiring, whatever it may be, now is a great time to say this.
So we don't need funding. We know what's best for us is like to talk with people who need to do things so we can understand better where we can try to have the most impact. So using Samson, trying to use it and see where it fails. And of course, I'll talk about it, but maybe what's most needed now is having people who integrate their work, their research inside Samson. Because we see tons of fantastic tools and we cannot do everything. And the whole point of the architecture, of the open architecture, is for people to integrate things to make them more accessible and more combinable with other tools. And we think that's what's going to be the most impactful in the future, is like the possibility to democratize tools.
Great. We already have potential interest from Alexis here. And then now I'm asking Michael's last question, which is, how are you prioritizing integrating new AI stuff that comes out basically weekly versus improving the platform itself versus building extensions?
Yeah, we sleep less. So how are we prioritizing? I mean, doing discussions like this. That's, I mean, our main goal is to be useful. So we basically try to ask users, and based on their needs, we see what they need. Sometimes it's with the constraint that we have to run a business, but our goal is to be the most impactful. That was the main reason to transition from academia to research. So we prioritize based on what we think people are going to use the most, or what we are told by people what they want to use.
Awesome. Thank you so much for joining.
Thank you
can't
very
wait
much
to see you again in person at the workshop, where we hopefully drill a little bit deeper into the integration part of this. I also shared with everyone here the nomination form for future presentations. So if you think that someone should really present here their work, that could be you, please feel free to use the nomination form. Also, Feynman applications are open, as I mentioned at the beginning of this talk. Thank you so much, Stephane.
And thank you for the great discussion and great questions.
Yeah, this was really lovely. Thanks, everyone. Have a wonderful rest of your day and see you very soon.
Thank you very much. Bye.
Thank you.